As in the previous video showed, recursion is a process or object that refers to itself in such a way that the process or object is repeated. Recursive functions usually include a call to function itself and the indication of what value should be returned when the limit of recursion is reached. In this video, we'll emphasize how can we analyze the time complexity of recursion function. The guideline for analysis of a recursive algorithm is as follows. First, we have to decide a runtime growth function parameter indicating input size. Then we have to identify algorithm's basic operation. This is same as for non-recursive time complex analysis. Then we have to check whether the number of times the basic operation is executed may vary on different inputs of the same size. So the first three steps exactly is the same as in the non-recursive algorithm time complex analysis. Then let's check the first step. Set up a recurrence relation with appropriate initial condition expressing the number of times the basic operation is executed. In this step to define recurrence relation, this is very important and also it's very challenging if we give you a question, give you a problem, or even in the interview question. The last step based on this recurrence relation, and we need to solve the recurrence by backorder substitution or a master method. So in this video, we'll emphasize what is substitution methods and what is another we call the master methods. Okay, let's take a look at this example. Define the n factorial equal to 1 times 2 times 3 times many number times n minus 1 times n for n larger than 1 and 0 factorial equal to 1. The recursive definition of n factorial is fn equal to fn minus 1 times n for n larger than or equal to 1 and f0 is equal to 1. When we write the shorter code, you can see it's just 7 lines. Algorithm fn, if n equal to 0, return 1, or else return fn minus 1 times n. Now let's take a look what is the input size. Input size, of course, is on n, right? Basic operation here corresponding to take a look at this one. What is the statement related to recursion? And from there, we want to find the specific statement which involves the input size. We see the first statement, if n equal to 0, return 1. This is the base case. In this one, only one constant runtime. Take a look at the second line. Return f n minus 1 times n. We do not know what is runtime for f n minus 1, but we know this multiplication will take one-step calculation. Will take one-step computation. So the runtime for this multiplication we can count for 1, right? It's constant runtime for multiplication, and such that we see we can formulate this recurrence relationship. Especially we want to emphasize the number of times of a basic operation in this recurrence relationship. We see we do not know what is runtime for fn. Let's name as mn. We do not know what is runtime for fn minus 1. We name as mn minus 1. And this one we take one more time, one more step. So it's plus 1. And such that the basic recurrence relationship in runtime analysis and in factorial problem corresponding to mn equal to mn minus 1 plus 1, m0 equal to 0. and we want to find out is mn. And we see m here is just the one sign to represent the runtime for this factorial calculation. You can use any sign. You can use m, you can use f, you can use t. Really depends on the interest of the implementation. And to solve, given this recurrence, we would like to find out finally in the final is runtime. So we need to find out the mn, the formula for mn, which doesn't rely on this recursive definition. And intuitively, we can use substitution methods. Right? We replace mn-1 by the mn-2 plus 1. We replace mn-2 equal to mn-2 mn-3 plus 1, right? So you can use this substitution. Finally, you have m1 in plus n-1. So the result is mn equal to big O-N. There's another example is a very popular example, Haloid puzzle problem. And there are 3 poles and n disks of different size. The puzzle starts with a discus in a lead stack in ascending order of size on pole number 1, the smallest on at the top. The objective is to move the entire stack to pole number 3. Such to find the following rules. First rule, only one disk may be moved at a time. Rule 2. Each move consists of taking the upper disks from one of the pole and sliding it onto another pole. Rule 3. No disk may be placed on top of smaller disks. So the corresponding to we want to move the whole stack from pole A to pole C. But we have to move one disk by one disk and make sure always the smaller disk is on the top of a big disk. And this, if you recursively think about this problem, it corresponds to you wanted to move n disk from A equal to C, which could be decomposed to moving n-1 disks from A to pole B, and then move the last disk from A into C directly. So you got the largest disk in the bottom of the pole C. Then after that, we have to move this n-1 disks to C by using temporary pole A. Right? So it means that this task can be equal to 3 steps. First step, move n-1 disk from A to B. Second step, move the last element from A to C. And third big step, move n-1 from pole B to pole C. You follow the same procedure. The recurrences is equal to, recursive function is as follows. Mn equal to 2 times mn-1 plus 1, m1 equal to 1. This is recursive definition. And finally, we want to find out the runtime of this solution. And this runtime will not rely on recursive definition. And to solve this problem, we can consider this the tree structure. Or if you want, you can just use the substitution method. You see mn equal to mn-1 plus 1, replace mn-1 equal to 2 mn-2 plus 1. And then we will have 2 to the power of 2 mn-2 plus 2 plus 1. Then you follow the same procedure. You replace mn-2 to be 2 mn-3 plus 1. And such that you have 2 to the power of 3 mn-3 plus n to the power of 2 plus 1 plus 2 plus 1. And then you can follow the same procedure, find the pattern. We see in the end mn equal to 2 to the power of n minus 1, m1 plus 2 to the power of n minus 2 plus 2 to the power of 2 plus 2 plus 1. Based on the formula we show you in the part 1, and also the formula we posted in the canvas, we see this is equal to the big O to the power of n, right? Another example is very popular, which is people use a lot to explain recurrence analysis, and which is merge sort. Is one example of divide and conquer methods. And the merge sort, it is sorting one of the sorting algorithm. The idea here it is give you n numbers. We want to divide these n numbers into the half. And we follow the same procedure, divide into smaller one. And here you only have 2 elements in the group. Then in that case, it is we merge the last 2 elements, put them in the correct order, and such that you have a different smaller sorted list, sorted smaller sorted sublist of size 2. Right? It will not be beyond 2. It could be less than. Then after that, it is you merge the adjacent 2 teams to sublist, and then you continue to merge, because every time you got a sorted list, already smaller one, but finally when you after you merge, you'll find the big one. Right? This is corresponding to one of the example of a divide and conquer. Divide and conquer is general algorithm designed parallelogram. Divide corresponding to divide the input data S into 2 or more disjoint subsets S1, S2. Recur is solve the subproblems recursively, and combine the conquer step, combine the solution for S1, S2 into a solution for S. The base case for the recursion are subproblems of constant size. Analysis can be then using recurrence equations. So for merge sort to divide array into 2 halves, recursively sort each half and merge 2 halves. Since here recursively sort each half corresponding to follow the same procedure, but input instance size it is smaller. And the merge method, once you have a sorted list, to merge these 2 sorted lists, we only need linear runtime, right? Because you have 2 sorted lists, and from these 2, pick up the smaller one from the current position, pick up the smaller one compared to 2 elements in the sorted list from the beginning to the end, right? And you find the smallest one, place the smallest one in the first position of the new sorted list, and then move the pointer to the next place in this reduced sublist. And then follow the same procedure and find the smallest one, place it in the second position, and change the location of the reduced sorted list, and then find the smallest one. In this solution, this merge, since you have to check for each position in sorted list A and sorted list B, and place the element in the correct position. In that case, you really need to check if they have n elements in the total of these sublists, and then in that case you need to have n times, n steps. And let's see for this merge sort. This merge sort just like this is previous is the merge method. Here this is the sort method in the merge class, and you can see they have the sort method has been invoked for multiple times, although the parameter changed. And here we want to check for this merge sort what could be runtime. And with merge sort usually merge sort use n log n nested n log n comparison to sort array of level n, length n. But how do you know this should be n log n? How do you know this merge sort or any type of sort cannot has time efficient algorithm or the solution which has time efficiency better than n log n? The recursion is corresponding to Cn is less than or equal to Cn divided by 2 plus Cn divided by 2 plus n. So corresponding to, you can use different sign, right? dn equal to 2 dn divided by 2 plus n. So based on these recurrences, we draw the recursive tree. We see the dn to merge sort n elements. We have to sort the n minus 2 elements. We need to have is 2 merge sort for half size. The merge method, right? When you need to combine, this is just a divide. Once you divide into be smaller one in each level, we see what is the total, the runtime for merge solution. And we see for each level, since they needed to combine the elements of array, the size of all elements, the size of the array is n. So for each level merge procedure, they need to have n steps. And take a look at this recursive tree, and you will find out that if you have n elements, this binary division can cause log n levels. Each level, the merge method will take all n, and so this reason the total runtime could be n, big O, and log n. And you can also use the substitution methods to prove that. And we see, this is just one type of divide and conquer example, and it can be used. These methods can be analysis for the recursive algorithm, especially for divide and conquer, can be the algorithm with the following structure takes n log n time, right? Okay, so this is a merge sort. And here this is just an example with Tn equal to b if n small, n is less than 2, and if n larger than or greater than 2, Tn is equal to 2 Tn divided by 2 plus Bn. And now the question it is, what could be the runtime for this Tn? We see you can use a substitution method, and replace Tn divided by 2 to be 2 Tn divided by 4 plus b times n divided by 2. And you can continue to replace that. Then finally you have Tn equal to 2 to the power of I Tn divided by 2 to the power of I plus Ibn. Note the database Tn equal to b, the case occurs when 2 to the power of I equal to n. In that case, I is equal to log n. So this reason Tn equal to bn plus bn log n. We ignore the lower order term, then we have Tn is equal to big O n log n, right? And also have another method to easily be used. And for many divide and conquer recurrence equations can be represented as Tn equal to C if n smaller than D, or if n larger than or equal to D, Tn equal to A Tn divided by B plus Fn. It corresponding to the bigger problem cast into B smaller problem, and each has the size n divided by B. And but you may ask if they subcast into the B group. If it cast into different groups, each group is m divided by b. It is supposed to have B groups, and we say sometimes some group based on condition can be ignored. And let's make it flexible. We count for A is groups. Each group has n divided by b, and each group is each group of n divided by b elements. They will follow the same procedure on this smaller group n divided by b. And this is the recurrence divide and conquer recurrence equation. To solve this recurrence equation, they have a master theorem. In that case, you will compare with based on the divide and conquer method, merge sort method. We see the A and B, which decided what it is the recursive tree could be, right? How high this tree could be, because you divide each subgroup has n divided by b, and each subgroup will be n divided by b to the power of b, right? And you continue check only when the this remaining elements is quite smaller, right? It's smaller than d, that then you can directly do calculation, and such that this b decide how many levels could be. And this Fn is used to calculate the runtime for conquer solution, right? The conquer part. And such that you can imagine, since it consists of two parts, the conquer part and also the recursive level part, and such that it will check for different cases. If Fn is On log Ba, which corresponding to if Fn it is upper bound by n to the power of log Ba, then Tn will be bigger theta n log Ba, right? They pick up the big one. So it compare these two factors, two determinants, and choose the largest one for the runtime analysis. This is based on one of the beautiful property we discussed in the asymptotic order, right? Okay, so if we see Fn happening, tightly bound by n log Ba, log Bn, in that case, we'll see Tn is equal to the theta n log Ba log k plus 1 n. And in that case, you can use the Tn equal to Fn, or use the log n to the power of log Ba. Because here you only care about A groups, right? And each group you have to conquer. So this reason they will check for n log Ba log n, and we will have one of the slides, at least one of the slides to prove that. And the third rule, it is if Fn is lower bound by n log Ba, in that case Tn will be equal to theta Fn. This is what we have the must method. It's a kind of a cookbook approach for solving recursive recurrences of the form. And here A and B both are constants, Fn is asymptotically positive. N divided by b may not be integer, but we ignore floors and ceilings. Usually we would like to remember that you check if you found out recurrence relation Tn equal to a Tn divided by b plus Fn, then you check n log b, n log, you check what? You check Fn, we check the asymptotic order of Fn and n to the power of log ba. If it's upper bound by n log ba, then you use runtime, use Tn equal to theta n log ba. If Fn happen to be tightly bound by n log ba, in that case you have n log ba log n. If Fn is lower bound by n log ba, in that case you use the highest one, that is theta Fn. So here in these slides, we want to use recursive tree to prove they have different components you take care, and why in this master method they cast into 3 cases. So in this recursive tree, you can see Fn to solve the problem of input instance size n, it can be cast into different groups. Each group is n divided by b. You have these groups. To conquer these a groups, we need to have conc runtime a f n divided by b, right? And then this procedure for each subgroup, you can you will cut into another smaller subgroups, and each group is n divided by b to the power of 2, right? You also have a is a sub element, and since each is a previous subgroup, we are cast into another a subgroups, and we see to conquer all these sub problems, we have how many we have? We have a square times Fn divided by b square, right? Because in each group we have these groups, a n divided by b groups. Each group will cast into another a subgroup, which has the input size n divided by n b to the power 2, right? And such we have n square, this smaller group. To conquer that, we need to have n to the power of Fn divided by b2, right? And this partition will continue, this specific division will continue until go to the theta 1. There's have very little input elements. To sum up, since it's a conquer, is divide from the top to the bottom. When we conquer, we have to conquer for each level, and such that we have to sum up all this runtime here. So this is master method. So for the recursive algorithm analysis, we want to emphasize, give you a problem, can you, just like this, what we practice here, can you list a recursive function? And once you have recursive function, can you use the substitution method or use the master method to solve this problem, right? Just like here, right? You just need to remember that, and you check for given problem, you check which case it belongs to, and use the formula that came from there. I think this is what we emphasize in the book chapter. It doesn't give the specific more information about the master theorem. Usually in the face-to-face class, we will explain, we will draw the what is the specific formula in the class. I think that's all.